Have you ever just stopped and stared at the colors swirling in a soap bubble? Or maybe in an oil slick on a wet road? It's like a tiny liquid galaxy just shimmering right there. Well, today we're going to pull back the curtain and look at the amazing physics behind this everyday magic. And think about this for a second. Those incredible blues, greens, and purples, they aren't made of pigment. A soap bubble is just soap and water. There's no dye in there, no paint. There's nothing that's supposed to be making that rainbow. It's basically an illusion, but it's an illusion created by the fundamental laws of physics.
Which, brings us to the big question here. If there isn't any color in the film itself, how in the world are we seeing it? The answer, it turns out, is this incredible thing that happens when you trap light in a really, really thin space.
To solve this little mystery, we have to understand something about light that might not be super obvious: the fact that it acts like a wave. Honestly, this one idea is the key to everything we're about to talk about.
Okay, so this is where it gets really interesting. Just like ripples on a pond, waves of light can actually run into each other. And when they do, they can either build each other up or they can cancel each other out. This whole interaction is called interference, and it is the engine that's making all those colors.
So just picture this. You drop a couple of pebbles into a still pond. You see those ripples spread out, right? And where they overlap, you get these really cool, complex patterns. Light does the exact same thing. Every single ray of light is a wave, and it has high points, called peaks, and low points, called troughs.
Now, when these waves meet, one of two things can happen. If two waves line up perfectly, so peak meets peak, they basically join forces and create a bigger, brighter wave. We call that constructive interference. But if they meet up completely out of sync, so a peak hits a trough, they actually cancel each other out. That leaves you with dimmer light or even no light at all. And that's called destructive interference. These two ideas are absolutely crucial. So let's bring it back to our soap bubble. How does all this apply? Well, the wall of the bubble is what we call a thin film. It is so incredibly thin that it basically acts like a perfect little trap for light waves, forcing them to interfere with each other.
All right, let's follow a single ray of light. When it hits the bubble, it actually splits in two. Part of it bounces right off the outside surface, but the other part goes through the soap film, hits the inside surface, and then bounces back out. So now you have two separate waves coming from the same original ray, but one took a slightly longer path. As they travel to your eye, they come back together and interfere.
And this is the whole secret right here. That second wave had to travel a tiny bit farther, down through the film and back up again. And whether that extra distance makes its peaks line up with the first wave depends completely on two things: the wavelength of the light, which is what we see as color, and the thickness of the film at that exact spot. And this explains why we see those amazing swirls. A soap bubble's wall isn't the same thickness all over. Gravity and air currents make it a little thicker here, a little thinner there. So in a spot that's just a tiny bit thicker, maybe the path difference is perfect to amplify red light. And in a thinner spot right next to it, maybe it's perfect for blue. What you're really seeing isn't color on the bubble, it's a shimmering map of the bubble's own thickness. How cool is that? Now, this isn't just some neat party trick that nature does. We've actually figured out how to harness this exact same principle to control light and create some really amazing technology. Let's take a look at how this has been engineered into things we use all the time. Two of the biggest applications are anti-reflecting films, which you probably interact with every single day, and a really fascinating measurement tool called Newton's rings. You ever notice that faint purplish or greenish shimmer on your eyeglasses or a nice camera lens? That's an anti-reflecting film. It is a super thin layer that's been engineered to be exactly 1/4 of a light wavelength thick. That very precise thickness guarantees that the light bouncing off the top of the coating and the light bouncing off the bottom of it will be perfectly out of sync, causing destructive interference. And the result? Glare just vanishes. It's basically invisibility by design. And then you've got Newton's rings. If you put a slightly curved lens on a perfectly flat piece of glass, you create this tiny wedge-shaped gap of air. This creates a predictable pattern of light and dark rings because of interference. Opticians use this exact pattern to test lenses for microscopic flaws with unbelievable precision. They're literally using light to see the invisible. So, when you boil it all down, those fleeting colors in a puddle are created by the exact same physics that lets us make perfectly clear lenses. By controlling materials on a scale way, way thinner than a human hair, we can actually control how light itself behaves.
And that leaves us with a pretty mind-bending thought. We've already figured out how to make things invisible to certain kinds of light. As our technology gets even better at creating these atom-thick layers, what other properties of light could we control? What kind of new technologies could we build? The possibilities are really as vast and as colorful as the phenomenon itself.